The next section that we're going to talk about is controlling renders. And we're going to start with anti-aliasing. Now if we look at my scene here, all I have is a plane with a spotlight shining down on it against a blue background. So this is actually the rim of the spotlight. So let's look at our render globals. And just under anti-aliasing quality, you'll notice that we have edge anti-aliasing and then we have shading. So we actually have two types of anti-aliasing. One is edge and one is shading. Now the edge is actually solved before the shading anti-aliasing. And what that's going to do is determine what geometry is visible in that pixel. So if we go to a diagram here and we look at this geometry, think of this as a pixel, and when we sample or look underneath that pixel, we're trying to figure out how much of the geometry is underneath it. So when we start increasing our sampling, we're actually going to get a much better representation of how much of that geometry is covering that pixel. So let's go back to Maya and back to the render globals. Okay, so with edge anti-aliasing, we have some presets. We have low quality, which is 2 samples per pixel per object. Medium quality is 8 samples per pixel per object. High is 32 samples per pixel per object, and highest is also 32, but it enables something called adaptive shading anti-aliasing. So, I mean, as you start increasing your sampling, you're going to be increasing your render times as well. So let's just go ahead and try medium quality. So that's 8 samples per pixel. And let's do a render. Now, did I save that? No, I didn't. Okay, so what I'm going to do is I'm just going to save this image. See how that edge is nicely cleaned up? And let's just go back to that low quality. Okay, so that's the difference. If we look at this edge here, that's with 8 samples per pixel per object, and this is with 2. Okay, so that looks a lot better. Now, if you find that your edges, like you're not getting good results by using, medium or high quality, what you might want to do is you can override those values. Okay, so let's say you have edges flickering, you have thin geometry, something like that, where the 32 samples is not enough. You can override, and this is done on a per object basis. So if we just select our plane here, go to the attribute editor, under render stats, and turn on geometry anti-aliasing override, you'll notice that there's actually different levels now. So level 1 is 32 samples per pixel per object. Level 2 is 96. Level 3 is 288 samples per pixel per object. Number 4 is 512, and number 5 is 800 samples per pixel per object. So you're going to want to be careful about these levels. When you start using the higher levels, you're doing a lot more sampling. It's going to take a lot longer to render. Okay, but the nice thing about this is it is done on a per object basis. So you might get away with high in your render global presets, but just for those little pieces, you can maybe move that up. So the next thing that we're going to talk about is the shading anti-aliasing. And you'll notice that in our render here, the edge is looking really nice, but still that halo, that rim of the spotlight isn't so great. So let's open up our render globals. And so now what we're going to be interested in here is the shading anti-aliasing. I'm just going to turn that back to medium quality and just do a render. Okay, and just save that or store that image. So let's go ahead and increase the number of samples for shading. Okay, so we're trying to figure out what color a pixel is. So we're sampling the information that's underneath that pixel, and in this instance we're doing 8 samples. And do a render, and you'll notice that it's actually cleaned that up really nicely. Okay, so now we don't have this sort of jagged edge along our spotlight. However, this is probably not the best or most optimal way to sample for shading. So I'm just going to turn that back down to 1. The reason being is that we're taking 8 samples per pixel per object regardless of whether or not we need it. So if we look down here, which is a big area that's covered only by black pixels, we don't need to be sampling 8 times or 8 in that pixel 8 times to figure out what color that pixel is going to be. So that's rather wasteful. So we have something that's known as adaptive shading. So I'm just going to turn that back down to 1. And when we go to edge anti-aliasing quality, I mentioned that the highest quality, what that does is it enables this adaptive shading. So we'll just hit highest quality. And you notice some things have become ungrayed. For instance, the maximum shading here. That's become ungrayed. And the way that adaptive shading works is that Maya compares the contrast that it finds. So if we're looking at a pixel and trying to figure out what color it is, Maya compares the contrast of its 5 neighboring pixels against the pixel that we're trying to figure out what color it is. So if we look here, this is actually more like a minimum shading amount and a maximum shading amount. Okay? And if I just scroll down here, we have something called contrast threshold. Now, for purposes of simplicity, I know we have 3 values, an RGB value, but let's just pick one value. Okay, so I'm just going to pick a value of 0.6 as our contrast threshold. So remember 0.6 and 1 and 8. So minimum shading is 1, maximum shading is 8. So I'm just going to stow this and show you how that works. Okay, so this is a pixel that we're currently trying to figure out what color it is. And then what happens is it gets some kind of contrast value by looking at its 5 neighboring pixels. And then it compares the contrast that it finds here against that threshold value. So remember we said we're going to use 0.6 for the threshold value. So let's look at that. Actually, I don't want to use that one. I'll use this one. Okay, so if we just kind of plot this on a graph, the minimum shading samples is along the horizontal. So the minimum maximum shading samples is between 1 and 8, maximum being 8 samples that we can take per pixel. And then we're just going to put the threshold value just along the vertical. So we're going between 0 and 1. So we said we had a threshold value of 0.6. So what happens is if Maya finds that the contrast of that pixel that we're looking at, when it looks at its 5 neighboring pixels, if it finds that the contrast value between that pixel and its neighbors is, for instance, let's say 0.4, if we plot this on our graph here, basically what we're going to do is we're just going to go up. Okay, so Maya's going to take one shading sample. So we're only going to take the minimum amount of shading samples up to the threshold. Okay, so if it finds that it's 0.5, that contrast is 0.5, again, only one shading sample. If it finds that the contrast is high or higher than 0.6, let's say 0.8, then we're just going to move up our graph here and over. So we might be using at that point maybe 3 shading samples. Okay, so as the contrast increases, so we're looking at the pixel and its 5 neighbors, we're getting a contrast value, and if that contrast value is high, like maybe up here, again, it's just a straight linear up and across. So we might be using 7 samples per pixel. So we're not actually taking the maximum amount of shading samples unless we really need to. And the way that we figure that out is by comparing the contrast that we find against the threshold value. Okay, so right here. Now let's go ahead and just try a render just with what the default is here. So we're taking a minimum of 1 shading sample per pixel per object with a maximum of 8. Okay, so if we go ahead and render that, you'll notice that this still looks great. Okay, but it's going to be a lot faster to render because we're not having to take 8 shading samples, you know, back here where we don't actually need it, where there's absolutely no contrast. Okay, so this is adaptive shading, and it's definitely a great optimization feature, especially in terms of render time. So I'm just going to add an ambient light here. I'm just going to add an ambient light in the scene, and I'm just going to move it up a little bit. Oops. And move that up a bit. And let's go ahead and do another render. You'll notice that what's happening here is that our problem is back. The rim of this light is actually not looking very good, so obviously we're not taking enough shading samples or something, just in this area here. So let's look at some of the presets that we have here. We have one that's called Contrast Sensitive Production, and if you just look at what happens with the contrast threshold values when I choose this, we'll talk a bit about what's going on. So I'm just going to choose that. Notice how all the values are lowered. And now, when we do a render, our problem is gone, okay? So that fixed it, just by lowering the contrast threshold value. So if we go back to our diagram here, what's happening is our contrast threshold value is, just for the sake of argument, let's say it's 0.2. So we're taking the minimum amount of shading samples until we find the contrast is 0.2, and then it's just a linear curve up, okay? So we're taking more shading samples in the scene where we need to. Because this is a low contrast scene, some of those values were actually slipping below the threshold value. So when we lower the threshold value, then we start taking more samples. And then that actually fixes our problem for us. Again, just like with the edge anti-aliasing, you can actually override on a per object basis the shading sampling. You just select the object, and just under the render stats, there's shading samples override, and you can just increase that. Okay, and again, the nice thing about that is it's on a per object basis. So just close that. The next thing that I wanted to talk about quickly was the use multi-pixel filter. Now what this does is it helps to eliminate roping or aliasing in certain rendered images. This isn't a post filter, it's a true filter. And just reducing these filter widths is actually going to result in less blur. So it is actually kind of a blur for the entire rendered image. So not just for the object that you're having trouble with, but the entire rendered image. The next thing I want to talk about is tessellation, and I'm going to bring up a file here. Okay, so I've just created a kind of curvy surface here. Now our renderer can't directly render NURB surfaces, so what it does is it converts the surface into many triangles, and this is what is known as tessellation. So the more triangles you have to describe the surface, the smoother your model is going to look. But the more triangles you have, the higher the render times. So let's just quickly look at tessellation. So I've just selected the object here, and I'm going into the attribute editor for it, under tessellation. And I'm going to turn on this flag, display render tessellation. Okay, so those are the triangles that Maya is going to use to describe this surface when it goes to render it. Now, tessellation is actually done in two passes. The primary pass divides the surface into an equal number of triangles. So if we look at this section here, the UV division factors, this is going to be the primary pass. So it's trying to divide it equally along the surface. And then the secondary pass, it uses more triangles adaptively based on the curvature of the surface. So where there's curvy bits, we're going to add more triangles. Now, right now, this would be the secondary pass. And I've turned off the no curvature check just so that you can see that we've got an even number of triangles here. And then when we start increasing that, you'll notice that the sort of flat area here, it still has a nice even number of triangles, but now there's more triangles placed on the more curvier areas of this surface. Okay? Now this section up here, it can be considered a basic or a simple set of controls, but we have a little bit more complicated set of controls. If you find that this isn't working, you can go into the advanced tessellation and turn on advanced tessellation. Okay? And I just want to point out that the attributes here are going to control that primary tessellation, so dividing the surface into an equal number of triangles. So I mean, when you start increasing the number U and number V, you're going to be increasing the number of triangles. You might get a really nice smooth surface, but you're going to increase your render times. So primary, and then this is the adaptive secondary tessellation. So just placing triangles where you need more triangle information, so for the really curvy areas. I just want to point out that you do have the option to turn on all three of these, but it's recommended that you don't do that because you aren't going to actually get a better looking surface at all, and it's going to take much longer to render. I just want to point out this use min screen. Now what that does is it tessellates based on how close the object is to the camera. So if the object is really close, see the number of triangles we're getting there? If I were to dolly out and just turn on the refresh tessellation, you'll notice that the number of triangles to describe the surface has gone down. So that's based on distance from the camera. Okay? One thing that you're going to want to be careful about when you are using this is that sometimes, because the tessellation is changing on a per frame basis in this instance, sometimes your specular highlight can actually change a little bit, do a little flicker. So that's just something to be aware of if you are going to use the use min screen. In terms of optimization for your scenes, we have a couple of controls under rendering. Render diagnostics. So the render diagnostics is going to give you information about how you can save render time. In the Hypershade, make sure that you use under the edit menu, there's a delete unused nodes. Just getting rid of the stuff in the Hypershade that you don't need to use. And then just file optimize scene size. Okay, so that will, again, it will get rid of certain nodes and curves, etc., that you might not want to have around, that again can just help increase, decrease your render times. One thing about this function is once you optimize it, you can't go back. So you might want to save your scene before you actually go ahead and optimize the scene. With the mental array for Maya sampling, it's adaptive, meaning that the algorithm attempts to use the fewest number of samples to achieve the best quality image. So I'm just going to do a render here. You can see our image is actually looking pretty good right now. But let's go into the render globals. Okay, so just under the mental array tab here, we have an area called sampling quality. So this is where we're going to control any kind of sampling or improvements to our image. Now, basically, if we look at the contrast section here, starting with the minimum level of sampling, what happens is an image is broken into blocks and then sampled at the corners. Now, these blocks, or the result from these blocks, are then compared with neighboring blocks. So that's a lot like what happens with the Maya render, except what's happening here is we're using a block. So we can be using, for instance, we can be using a 16 by 16 pixel block, sampling at the corners, and then comparing it with the neighboring block. And some kind of contrast value is going to be returned from that. And then what happens is that if the contrast is higher than the contrast values here, which really acts like a threshold, just like the contrast threshold in Maya, what happens is that if the contrast is higher than the values here, then further subdivisions are made. And basically this process is repeated until the contrast between the blocks is lower than the threshold values, so lower than this, or the maximum sampling value has been reached. Just a rule of thumb though for best results, if you're having trouble getting good image quality, try using high threshold values and then using lowest possible sampling values, okay? So lower these values as well. So if I were to lower this to -1, right now what this is a minimum sample of -2 and a maximum sample of -1. And if we just do a comparison there, you'll notice that there's a big difference, okay? So this is with a maximum sample of 0 and a minimum or a maximum sample of -1. So just in terms of what's happening with the samples, let's go back to the render globals here. Basically, if the sample limit is less than 0, then there's going to be fewer samples taken than there are pixels. So there might be one sample for every 4 pixels. Now this is called infrasampling. If this value is greater than 0, then there's going to be more samples taken than there are pixels. So there's a good chance that each pixel might be sampled more than once. And this is called oversampling. So just to kind of run down some of these values with regards to blocks and pixels. When your minimum sample is at -2, you're going to get a block that will contain 4 by 4 pixels with one sample. If this is at -1, you're going to get a block that will contain 2 by 2 pixels, so 2 pixels by 2 pixels, a 2 pixel by 2 pixel block, with one sample. Okay, so we're really not getting a lot of information about what the contrast or the color is of those pixels. Now, if the value is 0, each pixel is going to get one sample. When the value is 1, the pixel, each pixel will contain 4 blocks with one sample for each block. So basically the pixel is going to be divided into 4, and each one of those blocks is going to get one sample. So that'll basically be 4 samples per pixel. And then if the value is 2, for instance, so let's say a maximum value of 2, what's going to happen is the pixel is going to be divided into 16 by 16 block with one sample for each block. So you have the potential for that one pixel to have 16 times 16 samples, which would equal out to about 256 samples for that pixel. So obviously, I mean, you're going to get a really good idea of what color that pixel is because you're sampling it or you're looking at it so much, but you're also potentially going to take a hit in the render. Okay, so with regards to jitter, what jitter is going to do is it's going to slightly randomize the sampling points and try to help eliminate some of the artifacting that can happen, such as mock banding. So if you're still getting aliasing occurring, as I mentioned before, try lowering the contrast threshold values before increasing the sampling values. Okay? So what happens when you lower these threshold values is that it's going to cause more samples to be taken only in the problem areas, while the rest of the image is going to be sampled at the lower rate. So sometimes, you know, you might even want to use a value of 0.05 in here. So something like 0.05 might be necessary to avoid artifacting. So if this doesn't help, then you'll want to come in and use your jitter. So randomize those pixel or points before you start increasing your sampling. Okay? So lower your values first if you're not getting good results. Then still, if you're not getting good results, turn your jitter on before you start, you know, increasing your minimum and maximum amount of samples. The next section that we're going to talk about is the approximation editor. Now, by default, Maya's tessellation will be used unless you specify otherwise. So if I select this NURB surface and go under Window, Rendering Editors, Mental Ray Approximation Editor, you'll notice that there's 4 different approximation nodes that we can use to place triangles or tessellate for the mental ray for Maya renderer. So this first one is surface approximation. Now this is just a general tessellator for any kind of NURB surface in mental ray for Maya. The trim curve approximation, what that's going to do is place triangles, you know, around trim areas, so more triangles around trim areas. And then the displacement approximation is going to attempt to place triangles only over the displaced areas, so areas where we want to capture a lot of detail in a displacement map. So what happens is you could potentially have, for instance, a surface that's flat, that has a complex trim curve in it. And so in such a case, what you would do is you would specify a low-quality surface approximation. So we'd actually create a low-quality surface approximation for that. Okay, and if we just go to the attribute editor for that, you'll see that there's a number of options that we can use to increase or decrease the number of triangles that are placed over that surface. But you know, if this also had a trim curve, we could also add a trim curve approximation node to that same surface and edit that as well. Okay, so what's going to happen is that you would get a proper number of triangles placed over the flat areas of the surface, and then more triangles placed adaptively over the trim curve area, so that you're not, you know, wasting triangles, placing a lot of triangles all over the entire surface. So just adaptively being placed where they need to be. Now the approximation presets, it's just a drop-down menu that's going to provide the user with some of the useful tessellation settings. Okay, and the approximation methods, this is basically going to determine the criteria the tessellator uses for determining a triangulation. So there's more detailed information in your book about this, as well as on the Lobbyist project on our website. If you go to our website at www.aliaswavefront.com, under Maya Support, if you go into the eSupport site, there's a mental ray section. It's called the Lobbyist project. And there's a number of movies there, and one of them goes over the approximation editor in a lot of detail. So I would suggest that you actually go there to get some of the information as well.
Mental Ray has a handy little piece of functionality called Mental Ray Diagnostics. And this is a set of tools that is used to troubleshoot and refine render efficiency. These software renders provide visual, statistical information in the form of dots and lines, etc., that can be used for render debugging and optimizing. And this functionality is found in Render Globals in the Mental Ray tab towards the bottom, just in here under Diagnostics. There's 4 different ways that it can be used. We can use it to diagnose samples, in which case it'll be evaluating this section up here under anti-aliasing quality. We can also use it to diagnose a grid based on object, world, and camera space, photon emission, and we can also use it to diagnose the BSP or binary space partition tree for those scenes that are very large where memory usage is a problem. We can use this to tune and adjust the BSP settings down here in memory and performance. So let's start off by doing a diagnose samples render. So that's going to be evaluating the min and max samples as we have up here. Right now they're set at default, -2 and 0. And let's go in here and do a software render. Okay, here's our software render. Just going to enlarge that slightly for you. When we're using the diagnose samples mode, resulting image is a grayscale representation of sample density. So the black areas indicate no samples, while white areas indicate maximum samples as described in the Render Globals min and max sample levels. Now this red grid here is the task size or boundary size, and these are the tile sizes that the software uses to create the actual image, and this is by default set at 0 down here in memory and performance, which means that Mental Ray will come up with a task size that it deems appropriate for the resources at hand and the size of the scene. Typically that's 28 pixels, 32 pixels, somewhere in there in size, and that's what we see here. The next diagnostics mode that I want to show you here is the diagnose grid. It's found in this section in here. And this mode is used to depict X, Y, and Z axes with red, green, and blue lines in object, world, and camera orientations. This mode provides distance and size information between objects and is used for debugging. So let's do a software render with that enabled to world. We also have an option here for the width of the lines. We can adjust that in here. So I'm going to do a software render. And here we see, I'm going to maximize that image for you and dolly in. So here we see this red, green, and blue grid work, if you like, of lines. And it's used for scene debugging, for those problem scenes. The next diagnostics option we're going to look at is the diagnose photon option here. And this is used to optimize the number of photons being used. There's 2 modes, density and irradiance. Density and irradiance. And we also have a photon density field here. Right now it's grayed out. If we turn it to density, that field becomes enabled. The photon density is the averaging of red, green, and blue irradiance components, and the photon irradiance is the total incoming illumination. So let's just do a software render here with this turned on, and we're going to change the photon density from 0 to 100. And let's go over here and do a software render. So let's have a look at these colors here. Just maximize that image and dolly in slightly. And I'm just going to close down Render Globals. So we can have a good look at this. So once rendered, areas that are blue indicate no photon density at all, which makes sense because what we're looking at right now is the caustics that are being generated by the glass sphere in the scene. Areas that are red indicate photon density values entered, and by that we mean, let's open up Render Globals again, this value in here, 100. So the range in color values in increasing order of photon density is blue for none, cyan, green, yellow, red, and finally white. So let's just dolly into this section in here, and we see blue, cyan, green, yellow, and red, and then finally white over in this section in here, meaning that the number of photons in that area is exceeding the caustic accuracy statement in here. The last mode is the diagnose BSP mode. This mode gives a visual of the BSP, or binary space partition tree. Basically, the BSP acceleration algorithm breaks down scene geometry into an organized structure of recursively arranged voxels or volume elements. Now, these voxels are placed by the algorithm into a nested or recursive pattern. From a conceptual standpoint, this recursive structure resembles a tree with a main trunk, the initial voxel, and then the many branches as the geometry is recursively placed into the voxels. Now, there's two modes of operation. There's the depth and the size. Let's do a software render with the depth option enabled. And going to maximize that image and dolly in again. And what's happening here is that the blue areas indicate a very low recursion level in the BSP tree. And the color range goes through cyan, green, yellow, and finally red. And we don't see any red in this scene, and that indicates that the maximum BSP depth here hasn't been attained in the recursion of the geometry in this scene. So if we had reached a recursion level of 40, we'd start seeing some red areas here where the geometry count is very high. The mental ray from Maya map visualizer is a useful visual cue for understanding and refining the output of global illumination photon mapping as well as final gather. The information is available to users interactively in a camera or perspective window. Prior to Mental Ray for Maya version 6, the visual feedback would have been done for photon mapping using the Render Global's diagnostics functionality, and in the case of a final gather, you'd have to use the Mental Ray standalone application. So the visual feedback from the map visualizer can be quickly identified and understood using the map visualizer. The results can be used for faster tuning and more efficient rendering. So let's just make sure we've got final gather turned on. We do just 100 final gather rays. And we can scroll down to the Enable Map Visualizer section and enable that and do a software render. And we'll see over here in the interactive, in the perspective window, I'm going to maximize that window and dolly around. You see a very fine network of red dots here. We're going to just adjust the size of those dots or sample points that are used for the final gather calculation. Go to Window, Rendering Editors, Mental Ray, Map Visualizer, and we can increase the point size here so that we can more clearly see the final gather sample points as well as the normal scale. So it's quite interesting to note that this section behind the sphere doesn't have any sample points from our render, and that the sample points increase in intensity in this section over here.